So let's consider this circuit. Um, this contains a capacitor and an inductor. Notice there's no EMF source, there's no battery here. But we are going to let this system be in an initial state where the capacitor is fully charged. How did we get here? Well, probably we have an EMF somewhere and we charged the capacitor and then we flipped a switch and took the battery out of line and put the inductor in line. However you want to imagine that we got here, we're in a situation in which we have a fully charged capacitor and an inductor, and we are looking at the system right when I close the circuit and the capacitor is going to start to discharge. So we've basically taken a snapshot here where the capacitor is fully charged, but no current is flowing as of yet. Like the micro, maybe the femtosecond after I close the switch, and charge is not flowing yet. So no current is flowing. However, I do have a fully charged capacitor. Therefore, I have energy stored on the capacitor, right? I have 1/2 Q squared over C, which is UC. I have energy stored on the capacitor. Now, let's walk through the system as it starts to discharge. Well, it starts to discharge, current begins to flow. Now, we know what's going to happen. If the inductor wasn't here, right? If I just had a capacitor discharging, we know what's going to happen. The charge is going to flow off of the capacitor. When the capacitor is fully discharged, the current will stop flowing because it behaves like a decaying exponential. But now I have something else in line, the inductor. What does the inductor do? The inductor resists any change in the current. Well, it resists change in the magnetic flux, but what that works out to be, since the magnetic flux is produced by the current, is this resists changes in the current. So what's going to happen? Well, this is going to start to discharge, and the inductor is going to induce an EMF that tries to slow the current down, or it tries to stop the current. It fails. The current continues to flow, but let's look at the system right when the capacitor is discharged. Right? What has happened in the inductor? Well, I've induced a magnetic field. Therefore, I have energy stored in the inductor. Right? I started out with all this energy stored on the capacitor. As it discharges, the energy stored on the capacitor goes down, but energy can't just disappear. Where does it appear? It appears in the magnetic field of the inductor. So at the point where the capacitor is completely discharged, I have UL 1/2 Li squared. I have the energy completely appearing. This should be an L, this should be a C, that kind of look like a C. The energy has now been completely transferred to the inductor. Fair enough. Now what happens? Well, if there were no inductor, then we'd be done. Well, there wouldn't be any energy here, right? But we'd be done. The current wouldn't flow. But now I have this inductor which seeks to oppose any changes in the current. As it was, the current was flowing and it tried to stop the changes. It didn't work, but it did mitigate the current. But now, whereas the system would stop if it was just a capacitor, the inductor actually keeps the current flowing. And so what happens? Well, charge has leaked off. If you want to imagine the positive charge on this plate, the positive charge has flown off. It goes to the inductor. The capacitor is discharged. But the inductor requires that the current keeps on flowing. And so that positive charge keeps on coming around and then redeposits itself on this plate. That is going to continue until the capacitor has recharged. The inductor makes the current continue. So if you think of positive charge starting here, the positive charge flows around and redeposits itself here. And then after it's fully charged, it stops flowing and things happen again, but in reverse, right? After it's fully charged, this charge doesn't want to be there. but nothing is now forcing it to be on there because when the current stops, the EMF here is stable. The EMF is 0. So this charge will start to leak back off. Of course, the same process happens. I now have a current, and I have a changing current, which induces a magnetic field, which then keeps that current flowing after it would normally stop. And this capacitor charges back up. And so that if you're looking at the positive charge on the capacitor, it just kind of bounces around from one side to the other. I charge, a discharge, a charge, a discharge, a charge, a discharge, and so on and so forth. If you're looking at this from an energy standpoint, the energy is always split between the capacitor and the inductor. I've given you a small q and a small I here. Remember, that's our symbol for charge and current as a function of time. So this little one indicates that the charge on the capacitor changes in time. The little I indicates that the current changes in time. Of course, at its max value, I would substitute that with a large Q, and that's the total charge on the capacitor. At its max value here, I would substitute a capital I, and that would be the max energy stored on the inductor. But as it is, at any given point, the energy, the total energy can be found by adding up these two. So if I do that, if I say that the total energy is equal to 1/2 Q squared over C plus 1/2 Li squared, I have a form of the energy which may look a little familiar if I make a few substitutions. First of all, let's recap what we've said. What is my charge doing? It's bouncing back and forth, right? Very literally, it's oscillating. If this capacitor is charged positive, with the positive charge on the left side here, it leaks off and then comes back onto the right side. Leaks off, comes back onto the left side. So the actual charges are oscillating around the circuit. Even conceptually, we're oscillating. We're storing energy here, and then it's leaking off into the inductor, and then it's leaking back, or not leaking, but it's moving back onto the capacitor, and then moving back to the inductor. So there is definitely an oscillation here. So just as an aside, let me write down something which maybe you have seen before. It might have been a few semesters, but I hope you've seen something at least similar. 1/2 mv squared plus 1/2 kx squared. What is this? This is the total energy stored in a mass on a spring system, where the mass on the spring is displaced initially and then allowed to oscillate. It's let go, and we're going to assume that the spring can stretch and compress, and so I displace a mass, and it comes back through its equilibrium point, compresses the spring, stops, comes through its equilibrium point, stretches the spring, stops, and just oscillates back and forth. This is the energy stored in the spring. This is the kinetic energy. When we first saw this, and I'm assuming there's no friction, there's nothing to bleed energy out of the system, and so this thing will just oscillate forever. Maybe not physically realizable, but that's the idea. Without friction, there's nothing to take energy out, and it will just move back and forth forever. I should point out, without a resistor here, there's nowhere where the energy is dissipated. We're not bleeding off energy. There's no ohmic heating. Nothing is getting hot if there's no resistance. And so the energy just goes back and forth forever. It's an oscillatory circuit. The solution to this was x of t is equal to a cosine omega t plus phi, where phi is your phase angle and omega is your angular frequency, right? The phi here is very often 0. This is just to make sure that we don't have to start at a certain point, right? So if I start looking at my system when I have it stretched to its maximum, the cosine is the obvious choice there. But if I let it go and then I start caring about the system as it comes back to its equilibrium point, even though it's going to move farther, right? But if I start caring about it here, then a sine function would be the better way to go, because I'm at equilibrium and the sine of 0 is 0. This phase angle, it just ensures that we can characterize the system at any point right? So we don't have to constantly be switching back between sines and cosines. And even then, if I start my system somewhere in here before it reaches equilibrium. So the phase angle here is normally 0 in lots of problems that we do, but it's here for completeness. But the omega is our angular frequency. For the physical system, omega was given as root k over m, where k is your spring constant and m is your mass. Okay? Well, let's form some analogies here between this solution to the mechanical system and see if we can come up with a solution to this electrical system. Remember, if I solve one equation, this actually turns out to be a differential equation. If I express v as dx dt, right, I get a differential equation here. And if I express q as di dt, I get a differential equation. So what I can do here is, by draw the analogy, come up with the same solution, just substitute in different variables. And so I can come up with the same thing, where I'll say this: the charge on the capacitor at any time t is equal to some q naught, that is the maximum charge, cosine omega t plus phi. Where my angular frequency now is not given in terms of a spring constant and a mass. And omega here is now 1 over LC. Root 1 over LC, I should say. This is handy because if I want to build an oscillatory circuit, these are macroscopic parameters that I read off of spec sheets. I buy an inductor of inductance L. I buy a capacitor or build a capacitor of capacitance C. I can determine the angular frequency of this oscillation just by macroscopic physical parameters. And so just almost without any effort, I did the effort in Physics 1, right? This is where we did this. With hardly any effort, just comparing these two systems, I get this handy equation for the charge on a capacitor, charge on the capacitor in an LC circuit at any time as a function of its maximum charge, which in this case was the initial charge, its angular frequency given by root 1 over LC, and time, of course, and an arbitrary phase angle if I need the phase angle. Okay, I can give you one more here. But if I remember that the current is defined as dq dt, and if I take a time derivative of this expression, I'm going to get equals minus omega q naught sine omega t plus phi. So I got this expression from analogy to my mechanical system. I got this expression just from applying the definition of current, which is the time derivative of the charge. Take the time derivative of this, you get minus sine from the cosine. Chain rule gives you this omega out in front. Q naught is a constant.